Hello student, welcome back. We are going to start our today's class. It is module 6, lecture 1. In this session, we will cover in satellite communication, MECE106A, Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Content: multiple access techniques. Multiple access technique. In this we will cover multiple access assignment, network architectures, frequency division multiple access, multiplex FDMA, single channel per carrier SCPC, time division multiple access, system configuration, synchronization in Tdma systems. Multiple access assignment and network architectures. Multiple access is the ability for several earth stations to transmit their respective carriers simultaneously through the same satellite transponder. This feature allows any earth station located in the corresponding coverage area to receive carriers originating from several earth stations. Conversely, a carrier transmitted by one earth station through a given transponder can be received by any earth station located in the corresponding coverage area. This enables a transmitting earth station to group several signals into a single multi-destination carrier. A communication satellite acts as a relay station and as a nodal point in the circuits connecting the earth station involved. It contains one or more transponder chains, each of which has the capability of frequency translating, amplifying and retransmitting the signals received from earth station in the system. Some remote control switching capability may exist between some of the transponder chains. Moreover, in some advanced system, onboard switching and processing OBP is provided in order to perform one or more of the following functions. Switching in frequency, time or space, that is to frequency antenna spot beams. Signal regeneration and processing, notably baseband processing. In fact, the available information transmission capability, traffic capacity of a transponder chain is generally greater than that needed by a particular transmitting earth station. Therefore, in order to optimize the utilization of the transponder capacity, more than one earth station is allowed to access a transponder chain with either single or multi-destination transmission, which is precisely the function of multiple access. Three main modes of multiple access can be implemented. Frequency division multiple access FDMA, where each concerned earth station is assigned its own carrier frequency inside the transponder bandwidth. The time division multiplex access Tdma, where all concerned earth stations use the same carrier frequency and baseband with time division. That is to, they do not simultaneously transmit their signals. Then code division multiplexing CDMA, where all concerned earth stations simultaneously share the same bandwidth and recognize the signals by various processes such as a code identification. FDMA can be associated either with analog or digital modulation. On the contrary, Tdma and CDMA need practically to be associated with digital modulation. Contrarily to FDMA or CDMA, in which continuous signals are transmitted, in Tdma the signals are time shared, that is are carried in the form of non-continuous burst. The three categories of multiple access may be combined. For example, low or medium bitrate Tdma carriers can be shared. In FDMA the same transponders, and the same is true with CDMA carriers. There are also two different modes for assigning the communication channels in the transmitted carriers. Pre-assignment multiple access. In PAMA, in which the channels required between two earth stations are assigned permanently for their exclusive use. Demand assigned multiple access DAMA, in which the channel allocation is changed in accordance with the originating call. The channel is automatically selected and is connected for transmission only while the call is continued. This approach substantially increases the efficiency of the satellite transponder utilization and more generally of the whole communication system in comparison with PAMA. DAMA can be associated either with FDMA or TDMA and with analog or digital modulation technique. So, frequency division multiple access. FDMA was the first multiple access technique employed in satellite communication because of its simplicity and flexibility. It remains very commonly used. In FDMA, a different frequency is allocated in a transponder to each carrier, possibly multi-destination, to be transmitted by an earth station and then a given bandwidth. In proportion with the carrier capacity is also allocated. Therefore, the satellite resource is used in common and it will be shown in figure 6.1. So this figure shows a frequency plan of a satellite transponder for FDMA transmission. So in the x-axis it is frequency and in the y-axis it is power density. So transponder bandwidth is considering guard band and also different carriers. So total bandwidth of the transponder is different carrier as well as guard band. Detrimental effect of this type of multiple access is that due to nonlinearities in the transponder chain and notably in the power amplifier, simultaneously transmitting several carriers in the same transponder cause intermodulation between these carriers, resulting in unwanted emission intermodulation products. In order to reduce the level of such interference, it is necessary to keep the transmitted power significantly lower than the maximum available power saturation. This is called backoff. Furthermore, the power transmitted by each earth station need to be controlled. FDMA may be implemented with various modulation multiplexing methods. The most common methods being FDM-FM analog technique, in which carrier are frequency modulated by a carrier frequency division multiplexing baseband signals. Tdm Psk, it is a digital technique in which carriers are Psk modulated by a time division multiplex baseband signals, SCPC, for earth station with small traffic, in which each individual telephone or data channel modulates the carrier either by FM analog or Psk digital. Multiplex FDMA. In multiplex FDMA or Tdm FDMA, each carrier is assigned a separate non-overlapping frequency channel as shown in the figure. Power amplifier intermodulation products are controlled to acceptable levels by appropriate frequency selection or reduction of input power levels to permit sufficiently linear operation. Although such a control may also be needed in medium and high traffic earth station, this is particularly critical in satellite transponder where the output power is very important and costly parameter. Output backups are up to 3 dB. 50% reduction of the output power could typically be needed. Signal distortion and adjacent channel interference are also be accounted for. The text of the guard bands depends in part of the residual sidebands in each transmitted signal. They must also take into account the frequency drifts of the satellite and of earth stations, local oscillators. Doppler shifts of the satellite can also be significant for very low data rate transmission. Calculation of the effects of the intermodulation products created by satellite and earth station amplifiers must also take into account changes in relative signal strength received at the satellite due to possible variation in the EIRP, rain loss, antenna pointing, deviation, etc. of the earth station. FDM, FM multiplexing and modulation are dealt with communication engineering also as concern multiplexing equipment and baseband formats. In pace with the current trend towards a general digitization of telecommunication and also towards ISDN networking, FDM, FM, FDMA, the first and once dominated technique to the implemented in satellite communication, especially in international communication, is now frequently replaced by Tdm Psk FDMA. In fact, the use of digital technique enables significant increase in capacity. Tdm Psk FDM can be extremely efficient for point-to-point and point-to-multipoint links and also gives the possibility to further increase this traffic capacity by implementing low bitrate encoding LRE, telephony and digital processing technique such as digital speech interpolation DSI and even digital circuit multiplication equipment DCME. In order to optimize the link budget and power bandwidth efficiency, forward error correction FEC techniques are very gradually applied. Since various coding methods are code rates are available, the use of FEC makes it possible to adapt the link budget design in a flexible way thanks to a trade-off between the quality BER and the occupied bandwidth. FEC encoding can be used either to relax the link budget parameter, that is to small earth stations, or to improve the BER of a given link. In conclusion, the possibilities of Tdm Psk FDMA are intermediate between analog FDMA and Tdma. As a result of the digital processing, LRE, DSI, etc., transponder capabilities can be significantly increased, that is by a factor of 2 compared to FDM, FM, FDMA. Although the potential capability of full transponder Tdma is even greater. Tdm Psk FDMA allows a easier transition of digitization in the equipment of existing earth station. It may be sufficient to change the FDM FM modems and of course the terrestrial interfacing including multiplexing equipment. Single channel per carrier SCPC. In a SCPC system, each carrier is modulated by only one voice or low medium bitrate data channel. In the case of voice telephony, the channel can be processed in a number of ways. Some older analog systems use compounded frequency modulation CFM, but most systems are digital PSK modulated, although some of them remain using conventional 64 kbps pulse code modulation PCM with 4 PSK or QPSK, carrier modulation 32 kbps ADPCM and low bitrate encoding LRE combined with powerful FEC schemes and with 4 PSK, QPSK or 2 PSK, BPSK are nowadays generally preferred, especially for domestic and very small aperture terminal VSAT systems. In voice transmission, the carrier is voice activated and this permits up to 60% power saving in the satellite transponder. The carriers are active only 40% of the time on an average. SCPC CFM system use bandwidth of 45, 30, 22.5 kHz per carrier, while bandwidth for digital SCPC Psk can be extended also from 45 kHz 64 kbps down to 22.5 kHz or even less LRE. A 36 MHz transponder can therefore accommodate from 800 up to 1600 simultaneous SCPC channels. It will be shown in figure 6.2. It is also possible in FDMA to share a transponder between a part used for SCPC carriers and another part used in Tdm carriers. Much more details on digital SCPC operation and each station equipped will be found. The assignment of transponder channels to earth station may be fixed, PAMA, or variable. In the latter case, Tdma, the channel slots of the transponder are assigned to different earth stations according to their instantaneous needs. SCPC systems are cost effective for network consisting of a significant number of earth stations, each needing to be equipped with a small number of channels, thin route or rural telephony. In the case of relatively heavy traffic, Tdm Psk FDMA system tend to be more economical. This is the typical frequency plan of satellite transponder for 45 kHz SCPC channels. There are several channels showing over there in a pilot carrier, and there are channel 1, 2, 3, 4, channel M, channel 399 to up to channel 400. In the both the side, it is the side of the pilot carrier, and both the side and the carrier, the pilot carrier is 70,000 kHz, and in the left side it is 52,000 kHz. In the right hand side it is 88,000 kHz. Time division multiple access. Time division multiplex access (TDMA) is a digital multiple access technique that permits individual earth station transmission to be received by the satellite in a separate non-overlapping time slots called burst, in which information or digital telephony is buffered. Each earth station must determine the satellite system time and range so that the transmitted signal burst, typically quadriphase PSK or QPSK modulated, are timed to arrive at the satellite in the proper time slots as shown in the figure. Signal timing and details of the signal formats are described below. It should be noted that bit rate of the transmitted burst is generally many times higher than the bit rate of the continuous bit stream at the input of earth station terminal. So it is shown over there. The ground terminal, it is showing by ABC, continuous multiplex bit stream, transmitted burst or burst position in a given instant. So it is going to satellite. So there are a lot of frames are transmitted at the same time. And the reference station, that is also counter tackling the same thing. Compared with FDMA, Tdma offers following features. The satellite transponder carries only one frequency carrier comprising the traffic from several earth stations. In consequence, there is no intermodulation caused by nonlinearity, and the satellite transponder can be driven nearly at saturation, giving more efficient use of satellite power. In Tdma, the capacity does not decrease steeply with an increase in the number of accessing stations. Typically, an 80 MHz transponder Intelsat satellite driven by a single Tdma carrier can support up to 1600 telephone channels at 64 kbps bitrate. Note that the application of DSI and DCME technique permits an increase of the transponder capacity by a factor from 2 up to 5, but this is not exclusive to Tdma, and as seen above, this can be implemented with any Tdma carriers. The introduction of a new traffic requirement and changes is easily accommodated by altering burst length and burst position. Tdma can be combined with FDMA by sharing transponder between one Tdma carriers and the others, that is to multiplex carriers. This mixed FDMA Tdma process will be discussed later. However, it is only when Tdma is used alone in a satellite transponder, that is to full transponder Tdma, that the full efficiency quoted above in 1 is obtained. As shown in the figure, this is system configuration in figure 6.4. In each Tdma earth station, parallel input signal are entered through terrestrial interface modules (TIMs) under the form of digital bit stream or of analogous streams, which are first digitized and are addressed to different receiving earth station multiple access function. The bit stream are assembled in the TIMs to form group of bits called subburst. Each subburst contains information originating from a given TIM and destined for a given receiving earth station or a given set of receiving earth station. The Tdma buffers convert this serial bit stream to a burst of data bits. In this burst, the subbursts are allocated separate portion of the transmit Tdma burst, following a group of bits referred to as the preamble. The burst is then converted to intermediate frequency signals by a modulator, that is generally by QPSK. So this is the figure, the simplified Tdma terminal transmit operation and data format. So Tdma buffers are showing over there from different source, the signal coming in the Tdma form, that is buffer, then PSK modulator, there is a Tdma timing, it tackles the timing of this, that is to synchronization. Then it is going to an up converter, and for a Tdma total burst of signal, the carrier and bit timing recovery sequence, unique word, order where, control bit, subburst number, there is traffic information in between, then it is subburst number n. And in the total bit stream, how the format is, it is going to preamble, then to the node C, from the C, and then the to B, and there is a portion A, and it is indicated in the figure C, B and M. So it is shown over there. In the receiving earth station in figure 6.5, the Tdma receiver demodulates each of the bursts from separate transmit earth station Tdma terminals, then extracts only the required portion subburst to recover through TIM separate serial bit stream. Figure 6.5 simplified Tdma terminal receive operation and data format. So this is the total data format. Format is showing reference burst, guard time, that is burst from node A, burst from node B and burst from node C, that is preamble. It is going to PSK modulator, then Tdma buffers, Tdma timing, and going through different bit stream. As shown in figure 6.6, the input signal to a satellite transponder carrying Tdma consists of a set of bursts originating from a number of earth stations. This set of bursts is referred to as a Tdma frame. The figure shows that a small time gap called the guard band is left between bursts to ensure that they do not overlap with one another. So RB is the reference burst, TB is the traffic burst, the guard band is 2 milliseconds or 120832 symbols, that is for QPSK in Intelsat specification. The first burst in the frame contains no traffic and it is used for synchronization and network control purposes. This burst is called the reference burst and is generally sent by a special reference earth station which is in charge of providing synchronization, monitoring and managing the traffic for the whole system. Each burst is periodically transmitted at the Tdma frame rate, which is generally a multiple of 125 microsecond, corresponding to the conventional pulse code modulation PCM sampling frequency of 8 kHz. In each traffic burst, the preamble is used to synchronize the burst and assist in controlling the networks. The reference burst contains only the preamble. In general, the burst preamble contains the following parts: a carrier and a bit timing recovery sequence, which has the function of providing the carrier reference and the bit timing clock required for demodulation in the receive terminals. A bit pattern called the unique word, which is used to identify the starting position of the burst in the frame for each receiving traffic, each station, and the position of the bits in the burst, and to resolve bit ambiguity of the received PSK carrier. Note that the transmit frame timing is generally obtained from the receive frame timing by adding a delay Dn, which can be provided by the reference station via the reference burst. Order wire bits carrying the telephone and other service information for interstation communication. Control bits carrying network management information. This section of the preamble is referred to as the control channel. A supplementary feature can be implemented in Tdma systems. This consists in extending Tdma operation to over several satellite transponders. In this case, for Intel Tdma standard, a single Tdma frame can correspond to different frequency, carrier frequencies and or polarization thanks to transponder hopping, that is to rapid switching in earth station Tdma terminals between the relevant transponder frequency or polarizations. Synchronization in Tdma systems. Several different synchronization problems are involved in the operation of Tdma system. To demodulate the input burst more PSK carriers, it is necessary to recover the carrier and bit timing within the recovery sequence at the start of each burst. Thus, the Tdma demodulation usually has a very high speed circuits for carrier and clock recovery. Another crucial synchronization problem arises in the burst transmission timing at each accessing station in order to prevent overlapping of burst at the satellite transponder. This control is called burst synchronization. The burst synchronization is performed so that each burst maintains a predetermined timing difference reference to the position of the reference burst at the satellite transponder. To achieve the burst synchronization, the following methods have to be studied. Global beam synchronization. The transmit timing error is detected at each transmitting station by examining the received signal sequence, which includes its own transmission as well as that from a reference station. Feedback synchronization. The detection of the timing error is performed at the receive station or the reference station, and the information on the burst position error is sent back to the transmitting station via the control channel. Open loop synchronization. A transmit timing is determined by knowing the range from each station to the satellite. It should be noted that in the first two methods, the synchronization is based on a closed loop method. The final method requires that the station is able to receive its own transmitted burst from the satellite. In the case of satellite switching Tdma, SSTDMA, where the downlink transmission uses several non-global coverages, spot beams, and additional type of synchronization is needed, since it is necessary to route the burst through the different spot beams according to their destination by means of a onboard satellite switching matrix. The Tdma frame has to be organized with a synchronous switching sequence in which one or several time slots of the overall frame are assigned to each coverage area. So we are concluding today's session over there. These are the references. So thank you. We are ending today's session.